Hello, students. Welcome back to Stats with Mats. It is our Friday homework review, but today I am also going to be introducing a new concept that should be applied at the very end of any ANOVA question that you answer, and that is called Eta Squared. So in the interest of keeping this video short and efficient, let's go right ahead and get started. Okay, so let's review what happened this week. We spent 2 straight days trying to understand how to do an ANOVA, and that ended up being a pretty complicated process. So you'll remember we had this example of 24 cities, and they were categorized into 3 groups based on the city's core economic function. All right, so 8 cities per group. That generated for us 3 group level means and 1 grand mean in an overall puzzle, an overall sample of 24 cities with a K, or a number of groups equaling 3. Okay, so when it came time to conduct the ANOVA test, we did the following 7 sub-steps to step 5. First, we had to calculate our group and our grand means. In the setup to this formula, that was already given to you, but it might need to be calculated by you in the future for homeworks and other things that you might want to be doing. Secondly, you used the group mean to calculate the sum of squares within the group. So we did that by taking each value, subtracting from it its group mean, squaring it to make sure we were free of any pesky negatives, and then summing that across, like, both within the groups and then the sum of squares for all 3 groups together. And that gave us the sum of squares within the groups. Then, step 5.3, we calculated the sum of squares between the group using the grand mean. So there, we took the group mean, subtracted from it the grand mean, squared it, and then multiplied by the number of observations in each group. In the case of our example, that was 8 for all 3 groups. Okay, that, when it was summed, gave us the sum of squares between the groups. Finally, we calculated our degrees of freedom both within and between. Then we divided sum of squares within by degrees of freedom within to get mean squares within. We then divided sum of squares between by degrees of freedom between to give us mean squares between. Yes, these words are losing meaning for me too. And finally, we calculated F by dividing by using the mean squares within and the mean squares between. So nothing too dreadfully complicated on the math. It's just a tedious process. It's just a pesky process in which a lot of little mini math errors can be made. And unfortunately, if you make a mistake calculating a group mean, or if you make a mistake calculating the sum of squares within the group, that does cascade downward and cause the answer to be wrong in numerous other areas throughout. But for those of us that did it right, which I hope was absolutely all of us, we reached an observed F. Our test statistic was 1.347. You will remember that ANOVA is a no-tailed test. Therefore, the value we calculate must be larger than the critical value. Using our degrees of freedom, we had obtained a critical value of 3.47. Is 1.347 greater than 3.47? It is not. Therefore, we fail to reject the null hypothesis, and we have concluded that there is no relationship between a city's economic function and the homicide rates within those cities. However, it's a word of caution that has to be addressed here regarding ANOVA. The null hypothesis, you will remember, is something that stated that all your group means were equal to each other, and those group means were equal to the grand mean. mu1 equals mu2 equals mu3 equals mu4 equals mu5 equals mu total. So we're making a lot of assumptions there. It's very possible that the group means for a couple of the groups in an ANOVA problem will not significantly differ from each other. But if one of them does, then that might be enough to trigger a rejection of the null hypothesis. even if it's just one group mean. If that group mean is bizarre enough and different enough, that will tell you that, yeah, okay, there is a relationship between the grouping variable and the dependent variable. However, that's a bit of that it's a bit of a misconception to say that the grouping level matters for everything, because it may just be that one particular group is bizarre, one particular group is weird in what it is causing to happen. No matter, ANOVA will not tell you which of the groups is responsible for this outcome. ANOVA will never do that, unfortunately. Only regression can do that. Regression will allow you to parse out the actual effect of individual variables in a much more effective way. And so in a lot of ways, ANOVA is actually the natural thing to do right before starting regression. However, on my syllabus, I have reversed its order with chi-square. So we do ANOVA this week, next week is chi-square, and that is because chi-square is significantly easier than ANOVA. And I feel it raises people's confidence after what is honestly a tough week with ANOVA. But keep this in the back of your head. Keep this in the back of your head that ANOVA will just tell you, is one of the group means different enough to say that, yeah, you have a significant finding here. In order to add more detail and nuance, you will need a different method. You will need a different hypothesis test, okay? So in order to understand just how powerful the grouping variable is, we can't know which one necessarily is driving the significant finding, but we can understand exactly how much total variation is driven within the groups. And even if you have a significant finding, but a low metric for what is known as eta squared, that will tell you that, yeah, this is a significant finding, but quite honestly, it's kind of weak. Or, yeah, this is a significant finding, and it is an incredibly strong finding that's happening within the groups, between the groups, pardon me. So that's the question we want to answer with eta squared. Just how important is that grouping variable? Eta squared measures the strength of an association, regardless of its significance. So we can calculate eta squared for a situation where we reject the null hypothesis, and we can also calculate eta squared in a situation where we fail to reject the null hypothesis. If you're wondering why I have all these pictures of elephants, look at the Greek letter for eta. Eta squared has that long tail on the second part of the N, which to me kind of looks like an elephant trunk. Right? So as a result, I like to call it elephant squared, but really you should know it as eta squared. This is a pretty simple formula, and it's why I was telling you to sum your between group sum of squares with your within group sum of squares, because you will need the total sum of squares in order to calculate this problem here. So it's the proportion of the total variation that's explained by the independent variable, which, the way we have set up our ANOVA problem, the independent variable is the grouping variable. If you get a ratio here that is less than 15%, even if that's significant, that's a weak relationship. If it's between 15 to 25%, it's moderate. Anything above 25%, that's a pretty strong effect of the grouping variable, because there's a lot of noise and chaos that tends to happen in real data. So anything above 25%, we can say, yeah, that's a pretty strong, that's a lot of variation that's being described by simply understanding how observations are grouped. So to do this, we will divide the total sum of squares into the between group sum of squares. Now, this will always produce a decimal. This will always produce a value between 0 and 1. It has to, because the value for between group sum of squares will always be a smaller number than the total sum of squares. It has to be, right? It has to be, because total sum of squares is the between group plus the within group sum of squares. So in order to do this right, we have to be adding between and within to each other, but we also have to be organizing the numerator and the denominator in the appropriate way. Okay, so let's revisit that ANOVA table from Wednesday. You will remember I calculated the total sum of squares, but I didn't do anything with it. SS total here is 373.68, whereas the between group sum of squares is only 42.45. Now, if you just look at that table, I can see that, yeah, all right, that's a pretty small number compared to the total amount of sum of squared variation in this data set. So when I look at it that way, 42.45 is only a small portion of 373.68. Maybe it's not that surprising that I failed to reject the null hypothesis, that this was not found to be a particularly significant thing. But using what I have there, I'm going to go forward and I am going to calculate this. So I'm going to need to do 42.45 divided by 373.68. Okay? So I'll give you a moment to calculate that in your notes. So a very simple division equation, eta squared is equal to 0.114. Now that is something you should then be multiplying by 100 to convert into a percentage. You're not changing it at that point. You're just changing the unit. You're not actually changing the interpretation. So here's my interpretation of eta squared. Based on this eta squared of 0.114, I conclude that 11.4% of the total variation in murder rates is explained by the city's economic base. Therefore, this is an insignificant and weak relationship. Wow, it's almost like I just described your own relationship. So to repeat what happened there, I took the between group sum of squares and I divided into it the total sum of squares. That gave me the percentage of total variation that's explained by the grouping variable. 11.4% of the total variation is explained by the city's economic base. Therefore, these two variables have, just like you, have an insignificant and weak relationship. All right, so with that in mind, I'm going to now go over the homework that we did for today, and I am going to also top it off with a discussion of eta squared at the end there, okay? So here was the problem that we were presented with. Based on previous research and perhaps our own experience, we have reason to believe that stress levels of college students will spike during both midterms week and finals week. So to test this hypothesis, we have collected longitudinal data from 5 college students at 3 different points in the semester, and we have asked them to quantify their stress levels. So let's think about this on a scale from, say, 0 to 15. Lower values correspond to lower levels of stress, and higher values correspond to higher values of stress. Can you conclude with 95% confidence that there is a relationship between the time of the semester and student stress levels? So I gave you this table here, which gave you everything you needed to do to get started. But clearly, even if you didn't know this was ANOVA, even if you didn't see my label at the top, it's a dead giveaway because I have a categorical variable with 3 or more categories, and I have an interval level dependent variable that I want to understand whether the grouping variable exhibits some type of an effect on what is observed within the group, okay? So step 1, what do you know? Okay, well, I know that this is an ANOVA problem, which means I need to list my group means and my grand mean. So all I did here, you can see at the bottom of the table, I calculated X bar 1 to be week 1, and that group mean is 4. X bar 2 for midterm week, that is 8. And X bar 3 for finals week is 13. And then I combined those 3 group means divided by 3, and I got an X bar total, or a grand mean, of 8.3. Okay, so that's all listed right up here in step 1 of what do I know? X bar 1 equals 4, X bar 2 equals 8, X bar 3 equals 13, X bar total equals 8.3. I also wrote down my sample size, which is 15, n equals 15, and my number of groups, k equals 3. And that right there is all I need to get started. I'll move my face over here. Oh, hey, look, now I'm over here. Step 2 was listing our hypotheses. Our null hypothesis is that there is no association between the grouping variable and levels of stress. So I wrote that as mu of week one equals mu of midterm week equals mu of finals week equals the total mu regardless of the week. The alternate hypothesis, very simple. Mu1 does not equal mu2, which does not equal mu3, which does not equal mu total. So you could have written this in like that, or you could have written this by saying there is a significant relationship between time of the semester and student stress levels. That would have been the alternate hypothesis. Or you could say there is no significant difference or relationship between time of the semester and student stress levels. Now, in order to calculate my critical F, I first needed the alpha level. No problem there. I took 0.05 right out of the instructions, which told me to calculate this with 95% confidence. I then needed DF1 and DF2. Degrees of freedom 1, you will remember, is K minus 1. So 3 minus 1 is 2. Degrees of freedom 2, that is N minus K. So I took my N of 15, subtracted the K of 3 from it, and that gave me a DF1, a degrees of freedom of 2, 12. Looking at my stats packet, I was able to identify a critical F of 3.88. And now the fun begins. I need to calculate student stress. I need to calculate sum of squares within the group. So you will see next to each group, week one, midterms, and finals, I have a column for xik minus x bar k, and then a second column for xik minus x bar k squared. So I took that x bar 1 of 4 for week 1, subtracted it from each of my student stress values here. So 2 minus 4 is negative 2, 3 minus 4 is negative 1, and so on. And then I squared each one to get to 4, 1, 9, 4, and 4. And the summation of those 5 squared deviations gave me 22. I then went on to do the exact same thing for midterms, except now I was careful to make sure I was subtracting 8 as the group mean here. So 10 minus 8 is 2, 8 minus 8 is 0, 7 minus 8 is negative 1, 5 minus 8 is negative 3, and 10 minus 8 is 2. I then squared each one of my observations there, of my deviation from the group mean to get to 4, 0, 1, 9, and 4. The summation of which gave me 18. That's the sum of squared deviation for the midterm week. I do the exact same thing using the group mean of 13 for finals week. That gave me a sum of squared deviation of 14. To get the total sum of squared deviation within all 3 groups, 22 plus 18 plus 14, or 54. You can see I have that listed here as sum of squares within the group. Okay, that right there is easily the hardest part of this. All right, now I'm going to move my face back over here because I like that a little bit better. Okay, so now I needed to do the sum of squares between the group. So let's start with the first group, week 1. That was the group mean of 4, right down here now. Group mean of 4 minus the grand mean of 8.3 squared and multiplied by the group size of 5, which the notation for that is NK. That gave me 92.45. I then took my midterm week value here, 8 minus 8.3 squared times 5, 0.5. So almost no difference from the grand mean there. And then finals week, which was a much bigger number here. 13 minus 8.3 squared times 5 gave me 110.45. If you made a mistake there, it's likely because you forgot to multiply by 5 by the group size for each one of those, or you might have screwed up the order of operations. You do in the parentheses first, then the exponent, and then the multiplication by the group size. Stick with the order of operations and it will not let you down. So I summed those 3 and that gave me a total sum of squares between the groups of 203.3. What was next was to normalize by degrees of freedom. So I'll just come down here just a little bit here. I took my sum of squares within the groups of 54 and divided it by my degrees of freedom within the groups of 12. That gave me a mean squares within the group of 4.5. And then I did mean squares between by taking the sum of squares between the group of 203.3 and I divided it by 2. That gave me a mean squares between of 101.65. And we are almost done. F equals 101.65. Let me just double check that. Yep, 101.65 divided by 4.5. That gives me 22.58. That's a large value here. So I ask you, is 22.58 greater than 3.88? Yes, it is. Yes, sir. So therefore, we reject the null hypothesis with 95% confidence and conclude you're all about to be extremely stressed in a few weeks, right? We conclude with 95% confidence that there is a significant relationship between the time of the semester and student stress levels, and student stress levels, okay? Now, what if we wanted to do eta squared here? Okay, well, we might find something very different than what we found with the weak and insignificant relationship of the first example that we've done. Okay, so eta squared equals 203.3 divided by 257.3. Where did those numbers come from? Well, 257.3 is very simply my sum of squares between plus my sum of squares within. So I divide 203.3, that's my sum of squares between the groups, divided by my sum of squares total, and I get 0.79. Therefore, this is a significant and very strong relationship. 79% of all total variation in student stress levels is explained by the time of the semester. Absolutely spot on in my experience, at least. And there was much rejoicing. So thank you very much for your effort, for getting your homework in here. And I wish you guys a great weekend. And we will be coming back next time with a discussion of chi-square. I find chi-square kind of tricky, but there's a lot fewer places to screw it up. And that's why students tend to like it a lot better than ANOVA or t-tests. So if this was very challenging for you, keep at it. I am more than happy to look at practice problems that you've done or to answer questions that you have. Just don't hesitate to reach out. If you feel very confident about this, I'm certainly looking forward to seeing you continue that as we move on to chi-square. So thank you very much. And I'll see you again soon.